Okay, so in this last video, we are going to introduce some more summation practice, talk about those sums, and also talking a bit about this more generic way of tackling problems like Fibonacci using this thing called the tree method. So I want us to start with a little warm-up problem, kind of reviewing some of the stuff we just talked about. So which of these functions is the best mathematical model for the runtime of this code? So I have a piece of code here on the left, and I have some options for the runtime on the right. So which one of these best describes the runtime function? Okay, so if you use the tools that we've talked about before, you'd start by probably starting at the inside of the loop and say, well, on the inside, there's one step. And then I see a loop there, so I'm going to add a times n, and I see another loop, so I'm going to add a times n. And so in total, I think this is going to be something like n squared. Turns out this is not going to end up working. We have to be very careful about the loop bounds here. Just because you see a loop does not mean it's going to incur n steps. It's only true if that loop is going to run n times. But this inner loop is really deceptive because it's running on different iterations of that outer loop. It runs a different number of times. And so we're going to need something more complex to model what's the runtime of this code than something really simple like f of n is equal to n squared. So that is not going to end up being our right answer. So we need to use these tools as a for summation to think about how do we actually go about counting the number of steps in total. So to think about this a little bit more precisely, the runtime of this code, well, that inner value still takes one step. But how many times does it run? Well, it depends on what I is, the value of that outer loop. So it's going to run kind of whatever the outermost loop is going to, right? If depending on what value of I is, that's what it's going to run to. And that outer loop runs a total of n times. So this inner loop, how many times does this inner loop run? Well, it runs 0 times the first time, then 1 time, then 2 times, then all the way up to I minus 1 times. Now, notice each time we get to that inner loop, it's going to go run off I iterations, right? Whatever I was. First it was 0, then it was 1, then it was 2. And so how do we model this part? How do we model this behavior of this changing number of iterations on each iteration of the outer loop? Well, we can use summations, right? We can use this notation for summations. This sequence here is a different sequence just to talk about what is a summation. The sum 1 plus 2 plus 3 plus 4 all the way to n, well, that's the sum from I equals 1 to n of I. Now remember, be very careful when you're writing these summations to think about what's the stop point and what's the start point, or start point and stop point. I guess I should put it in normal order. So I equals 1 is your start, n is your stop, because this summation on the left right here, this one I'm drawing out, starts at 1 and ends at n. But whatever you're trying to model, that helps you decide you need to decide what's the stop point and the start point. Now, when we are talking about summations, we usually think about them as being able to work for essentially any function that changes based off this index I that you're looping through. And so this kind of very, very generic definition of a summation, the summation from I equals a to b of some function f of I, well, it's going to be f of a plus 1 plus f of a plus 2, going all the way to b, and as you get closer and closer to b, you'll eventually end at f of b. So it's kind of the sum of all the values in between changing with I. So that's kind of our super generic definition of summations. And so the way we'll end up modeling this code snippet is with essentially a nested summation, right? Because on each iteration of the outer loop, which runs something like n times, on the inside, it's going to go and do some more steps. On the first time, it's going to do 0 steps. On the second time, it'll do 1. On the third time, it'll do 2, right? By first, I meant like when I was equal to 0. So this inner loop right here, this inner loop is being modeling this summation. Whatever I is, this is how much work it's doing. And we do that work for each iteration of the outer loop. That's what that's kind of getting at there, is it's trying to say we're going to do this multiple times. So looking at this, though, it is not clear what is the big theta bound. Like, is this n? Is it n squared? Is it n cubed? So what we need to be able to do is go from code to a summation. That's kind of part of our code modeling step. Then a second part of our code modeling step will be coming up with one of those closed form solutions. So looking at this formula that has this complex summation in it and seeing if there's a way to just find out, here's the formula for what this answer actually is, maybe very simple, so that then you can find a big theta from that. So what these normally look like, the way we normally will have you solve these problems, is once you come up with one of these sums, you're going to have to kind of massage them into a form that's usable. And so what we'll have for you, is a bunch of summation identities. And we can use those as essentially parts of our puzzle pieces to help us solve this grander puzzle. How do we starting from this point, get to a point that has a closed form? One thing I'll mention is, as I said before, we're going to show you a lot of identities, and we're just going to take them all for fact. We're not going to prove them. You don't need to understand why that they're true, but hopefully you'll start seeing patterns of when you can start applying them as you get familiar with them and you practice them more. So the first one we're going to use is we're going to use this one that's called the summation of a constant. So if you're looping from I equals 0 to k minus 1, adding up some constant c, another way of saying what that value is in English is you're adding c up k times because you include 0 and you stop at k minus 1. So c plus c plus c plus c plus c, k times, well, that's the same thing as just c times k. So we're going to end up collapsing this inner loop right here because it's just adding up the number 1. How many times does it add up the number 1? Well, it adds it up I times. 0, 1, 2, 3, all the way up to I minus 1. That happens I times. So this kind of inner summation is just going to get replaced with the value I. That's a summation identity. We're saying this sum is equal to this value. And then we'll just continue to do that. We'll apply another summation identity. So this one is going to say, you can factor out a constant. So when you are multiplying a value at each term of your summation, it's the same thing as pulling that constant out. This is similar to how when you, maybe in your algebra classes, you can like factor out like a common multiple of a sum and say, oh, it's just this constant value times the entirety of this sum. Another way you could have done this is you could have said 1 times anything is just itself and just dropped it entirely. We'll end up doing that. But we wanted to point out that this is another identity that's fairly common. If you're multiplying by a constant, it's very common to just pull that constant right out of the sum so that your sum is now in a kind of a simpler form that looks more like one of the identities we'll show you. So factoring out a constant, a very common summation strategy. So now we just have the sum from I equals 0 to n minus 1 of I. Now, this still is not a closed form. I don't know what the big theta of this is yet. But don't worry, we have yet another summation identity for this called Gauss's identity. So whenever you see the sum of i's, Gauss's identity is probably going to be the thing that's going to come to mind. And again, you're going to have a cheat sheet with all of these. So you should always be able to see one of these pop out and be like, oh, this looks like one of these things on the cheat sheet. Maybe I should apply this one. Gauss's identity says when you're adding up the numbers between 0 and n minus 1, that's just going to be the same as n times n minus 1 divided by 2. Very clever formula. Very clever closed form. And so now we can say, okay, this function, f of n, that used to be this nested sum, is now actually just equal to n times n minus 1 over 2. We're going to simplify this with algebra a bit. Multiply by n, like multiply the n out, and separate the terms. And now this is a simple polynomial that we are able to apply big O, big theta, big omega analysis to. And so now we can say, okay, this is surely big theta of n squared. Oh my goodness, lots of work to get from that nested sum to this big theta result. And so you'll get lots of practice trying out different summations and trying out applying these identities to kind of massage from point A to point B to get something usable. Now, really importantly, I want to highlight something. The first thing is you do not need to come up with these or explain why these identities are true. We just give you a list of them that you're going to be using in this course. So want to highlight that first. The second thing to highlight is you might be thinking, wait, Hunter, you just said on that item pool slide that this function was not n squared, but you just showed me here that it is n squared. Notice that it's theta of n squared, but it's not correct to say the function exactly is n squared, right? This thetas, big O's and big omegas, they are bounds. They're telling you how it scales as n grows larger and larger. they're not saying that the relationship is exactly n squared. Like if you have 2, it is now exactly 4. It's saying it grows n squared like. Remember, big O is an upper bound, big omega is a lower bound, and big theta we said is quote unquote exactly 2. But a better way of phrasing that is it's both upper bounded and lower bounded by the same function, meaning it grows like that function, but no statements about exact equality. So we would not say that this function is n squared. We'd say it's big theta of n squared, or it grows like n squared as n goes towards infinity. Okay, so that was a lot of stuff on summations, and we'll get lots of practice with summations. And we'll actually see in this next example some more summations that we'll use. What I want to introduce for our last part of this video is this thing called the tree method. So talking about kind of a more generic version of that Fibonacci example that applies in more contexts. So before I kind of explain what this tree method is, I want to highlight that we've been showing you in this class different tools for our recurrence to big theta toolbox. That's step 2, asymptotic analysis, taking a runtime function and turning it into a asymptotic bound. We've shown you 3 tools in this class, including the one I'm about to show you. The first one was master theorem, taking a recurrence, and it was fairly convenient, even though it was really weird looking at first. You could just plug in some constants and it works out fine. You get the answer. Now, the con here of master theorem is it only works in a very specific format of recurrences. Namely, you have to be dividing by your input, or your input needs to be divided every time. We also showed you how to unroll the recurrence, kind of start at the bottom and work your way up. And it's definitely one of the nice things about unrolling the recurrence is it's definitely less complex, right? You just write out some numbers, do a little bit of algebra. But it requires intuition to solve, like trying to just see the pattern and be like, oh, I know what the pattern is, I know how this scales. There's no real formal technique, it's all gut feeling, and so it's not going to be the best always moving forward because it might not handle every single case. So this last example, or last tool we're going to show you is the tree method. And this tree method is also going to work out really nice and well. It's easy to just plug in your values and work through it. However, it's going to take a lot of setup. And you still have to do some asymptotic analysis at the end because we'll end up with some summations. So it's going to be a little complex to set up, but it's a very general setup, so it works in a lot of contexts. So what we're going to talk about for the tree method is talk about that merge sort again. And again, we don't really care about the behavior of merge sort or what it's doing. All we really care about is its recurrence. 1 if n is less than or equal to 1, or 2 times t of n divided by 2 plus n otherwise. And the reason we want to talk about merge sort is before, when we talked about that Fibonacci-ish, we had constant work all over the place, so we got to be lazy. And now we have to be a little bit more particular because now there's kind of this non-recursive work that takes more time. So what we're going to do, like before, is draw out the function call tree. We need to figure out what's the input to each call, and then how much work is done in each call. And I said a little bit earlier, when I use this term work, I mean kind of the number of steps, but kind of concretely, when we're going to be talking about work, we're going to be talking about non-recursive work specifically. So how much work is done in one method call outside of those recursive calls. The reason we want to separate this work is because the way we're going to be counting all over the tree, we're going to be accounting for the work that's happening inside the recursion, kind of by counting other places in the tree. So really all we need to count is the non-recursive work and add that up all over the tree because all of the nodes will be added together. So where is this work coming from? Well, in the merge sort example, it's coming from the merging step. The actual big theta of n operation inside merge sort that processes the entire input. Oh, whoops, I did not mean to press that button. Hopefully I didn't break anything in the recording. What this means in our recurrence is this step right here. This kind of, the fact that we had to loop over the whole array, the fact that we did n steps or order of n steps, that is kind of where actually a lot of the work is coming from. And so we're going to call, this non-recursive work is really what the part that we care about. So that's what we're going to kind of go through and try to add up. So for merge sort, here was our recurrence. And we're going to kind of do a similar process to what we did with Fibonacci. How many nodes, or how tall is this tree? How many function calls, how many layers will there be in this tree entirely? Well, it starts at the input size n, and it keeps going while we can divide by 2. We keep dividing by 2 until we get one element. And so how many times can we do this? And so whenever you hear this, how many times can I divide by 2? That's when you might start thinking about this log n. How many halvings can we do? We could do log base 2 of n. So the height of this tree will be log base 2 of n. Now for this second question, we're going to ask something slightly differently than before. Instead of asking how many recursive calls there are at each level, what we really care about is how much work is done at each level. We're going to ask how much work is done in total across the whole level. And we'll see here that the amount of work will vary by function call, right? Each one's doing a slightly different amount of work depending on the level of the tree. But across each layer, it's going to end up being the same amount of work total, right? And so we're going to have some, in this example, we have n work at each layer. And this will be a little bit clearer when I actually walk through these calculations. So here's our tree. Here's our recurrence. Notice, importantly, I mentioned that we care about the work at each level. In order to figure out the work at each level, we're going to need to know the input size at each level. So we start with f of n, and f of n makes 2 recursive calls to f of n over 2. And those make 2 recursive calls to f of n over 4, et cetera, all the way down to 1. So we're going to have a bunch of recursive levels. We have 0, 1, 2, 3, all the way up to log n. How many nodes are we going to have at each level? Well, if we think back to that Fibonacci example, since we're doubling the number of recursive calls we make each time, we're going to be kind of doubling the number of nodes at each level. So it's going to be something like that 2 to the I pattern. And then how much work is done at each node? Well, since in our recurrence, oh, again, I pressed the wrong button. In our recurrence, the thing that matters for that work is that kind of plus n term. The work at each node is going to be its input, essentially, right? When this function has half the input, that n in this formula is really n over 2. So it's doing n over 2 work. The ones down here are doing n over 8 work in total. So at each node, they're really doing whatever the input is at that level. And since the input at that level was n over 2, n over 4, n over 8, each individual node at that level is doing that much work. But if we think about multiplying those together, how many nodes at each level times how much work is being done by each node at that level, we can see that there's going to be a constant level of work across each level of the tree. Kind of weird. But this kind of intuition for breaking down the problem into how many levels are there, how much work is being done across the entire level, and the way we figure that out is the number of recursive calls at each level times the amount of work happening at each node. And in this case, because they're balanced, they ended up being n across the board. Now, what I want us to do in order to figure out the total amount of work is I actually want to break this down into a sequence of smaller questions that will help us out. So notice here, our ultimate goal is to find what is the amount of work in the entire tree. But in order to get there, we're going to have to ask a bunch of smaller questions. Part of it is to explain how we got some of these numbers here. But the other thing is, how do we put them all together to figure out the work overall? So we start with our first question. What's the size of the input per call on level I? And so we saw here that, at each level, we kept having the input. So at the ith level, the input size is just going to be n divided by 2 to the I. How many times have I divided by 2 so far? Right? So if I divided by twice, 2 to the I would be 4. So in total, we're doing 1/4 of the work. Now, how much work is done by each node at level I in our recursive cases? Well, according to our recurrence, they do work proportional to their input size. So since their input size, their input size is n over 2 to the I, then their work, again, at the recursive levels is going to be n over 2 to the I. We'll handle the base cases later. Okay, so how many nodes are at level I? Well, we kind of talked about that one before. Since we're doubling the number of recursive calls each time, we're going to have 2 to the I nodes at each level. And if we want to figure out the total work done on level I in our recursive cases, we just multiply the answers to question 2 and question 3, the number of nodes at that level times the work per node. So 2 to the I times n over 2 to the I, that's just going to be n. Pause here for 1 second. what have we just done? We have just shown what is the amount of work done at each level of the tree in the recursive cases. Notice how, if it wasn't super clear before, like, oh, in that table, how did you come up with the number of nodes per level and the work per node? This is giving you a really methodical way of thinking about this. Computing the input size at each level, right? How many times we've had the input? What's the work done? You look at the recurrence for its input size. So now this should be able to generalize to different types of recurrences, maybe ones that have n squared in their recurrence instead of just n. Okay, so now we've just figured out what's the work per level, and in the recursive levels, it's always n. Okay, now we want to figure out essentially when are we going to hit our base case? How tall is that tree going to be? On what value of I does the last level occur? Well, we hit our base case when the input size is 1. And we already figured out from question 1, what is the input size on the ith level? So what we can do is kind of set up an equation here. Well, on the ith level, the input size is n over 2 to the I. So when is that equal to 1? Well, we can multiply both sides by 2 to the I, and then take the log of both sides to figure out, oh, that index I is going to be log base 2 of n. That's how we figured out how tall the tree is. Now, the last couple things we need to figure out is, okay, that's how tall the tree is, but what's happening at that base case? How much work is happening across that level of the base case? Well, in our context, if you look at our recurrence at the top, each individual base case node is only doing one step, one work. And so we have to ask, well, how much work is happening across that base case? Well, it's the number of nodes at the base case times the base case workload. So it's going to be our answers to 5 and 3. 5 is what index does the base case occur and what layer? And question 3, how many nodes at that level? Well, we plug those in together. We know that's going to happen at 2 to the I, and I is going to be log base 2. Then we answer question 6, which was how much work is being done at each of those nodes. It's 1. So 2 to the log base 2 of n, well, log and exponents are kind of are inverses of each other. And so you could kind of argue to yourself here that that's going to end up being n. Okay. So now we've answered a lot of questions, and it's probably not quite clear yet why we asked all these questions in the first place. But I promise you we're almost there. We can now put these pieces together. So remember, all the questions up to question 4, we're kind of figuring out how much work is happening at each of the recursive layers. Question 5 was asking how many layers are there in total? When does the base case happen? And question 7 was ultimately asking what's the amount of work happening at the base case? So to figure out the total runtime, we're just going to loop over all of the layers before the base case and figure out how much work is happening in all the recursive cases. And so here I have this sum where I'm starting at layer 0 and I'm going all the way to the base case. Remember, the base case happens at index log base 2 of n, and we want to stop one early because that layer is the base case level. Right now I'm only considering the recursive case. So I stop one early, and how much work is being done at each level? Well, I answered that in question 4. In question 4, we said it's n each time. Okay. Well, also we need to make sure not to forget we also have that base case. So we also do work for that base case layer, but we figured out in question 7 that's n. Now, one thing that's a little bit tricky here is this looks a little nasty so far, but one thing to notice is that we have a sum adding up n a bunch of times, and then we have plus one more n. So for example, assume that sum on the left had 4 entries. It ran 4 times. We had 4 n's plus an n. That's equivalent to saying 5 n's, right? So we can actually combine these two terms into one mega sum. Since that top left one stopped one early, and we have just one more n to tack on, we added 1 plus n for the base case, we can kind of simplify this into one big sum. And now we can apply one of our most common identities, which is the summation of a constant. Notice n is a constant with respect to that summation loop. That summation loop loops from I equals 0 to log base 2 of n. But the value we're summing up is not a function of I. It doesn't change on each iteration of the loop. So we can pull that constant out And then we can get the fact that this is really, or one way to do it is to pull this constant out, or to recognize that n is just a constant. We can use summation of a constant here to just say, oh, it's just that value times the number of time that loop's run. That loop is going to run log base 2 of n plus 1 times. And so we simplified our algebra to get n log base 2 of n plus n, which we pull together. The dominating term there is that left one. It is big theta of n log n. Oh my goodness, that was a lot. But we got to the same answer that we got to in master theorem. Now notice, this was one case where master theorem also worked. Notice how much easier master theorem was instead of this. But this is a very generic pattern that works for a lot more cases. And so we'll come back to this practicing in class for Wednesday and in section on Thursday, practicing how to get used to this, because I promise you, this was a lot to get through for this first time. But once we kind of have this framework of these questions, and now maybe looking back, you kind of understand why we asked all these questions, you'll be able to tackle, using this framework, more different types of recurrences. So now I want to do a quick wrap up before the end here. We have now armed you with a toolbox stuffed full of analysis tools. We learned about different ways of doing code modeling, right? We talked about simple runtime functions and case analysis and recurrences for recursive code. And then we talked about how to do asymptotic analysis, right? We talked about, there's our simple intuition of just dropping lower order terms and constants. We talked about big theta, big O, big omega. We talked about, for recurrences, how to use taking a recurrence and turning it into that asymptotic bound. So we have so many tools in our toolbox now for tackling algorithmic analysis. And now that you're equipped with this toolbox, you're now able to go out for the rest of 373 and talk about concrete data structures, analyzing them in different cases, analyzing them based off the algorithms we describe. And so we're going to be starting off this Friday with our first kind of new data structure, right? So far, most of the data structures we've learned have been reviewing what's in 143, but now we'll actually be able to do some analysis on data structures that we didn't really talk about in depth at the 143 level. So I'll see you all in class where we get to practice some of this tree method stuff.